and feature engineering. So hopefully you watched the lectures of today and the past couple days. Otherwise, you might be a little bit lost here. But if you haven't watched the lectures, by all means, please stay. At least you'll get help with the lab. So it says in this lab, we'll work through the process of implementing a linear model, defining loss functions, feature engineering, and then minimizing loss functions. And we're going to use the TIP calculation data set that we've been working with in previous labs. So you should be somewhat familiar with the data already. So the first thing we do, we load our modules, great. We load the data set, great. Bill, tip, sex, smoker, day, time, and size. I guess that's size of party. Doesn't really say. So question 1. In lab 6, we use the constant model. Now let's make a more complicated model that utilizes other features in our data set. So we're gonna predict tip to be a combination of the following features. We have total bill, sex, smoker, day, time, and size. Those are just the columns we see above. It says, notice some of these features are not numbers. That's correct. Sex is not a number, smoker, day, size, time. None of them are numbers. So that's kind of annoying, but we'll work through how to deal with that. That's what this lab is all about. So the first thing we do is we remove tip from our data set, because tip is kind of like, well, it's our response variable, which means that we're going to use everything else to predict tip. So when you're building a linear model, it's usually helpful to have all of your X variables, so to speak, in one array or one data frame, and then your Y variable, in this case tip, somewhere else. So that's exactly what we do here. We make tips, we define it as its own thing, and then we drop it from the original design matrix. So that's just setup, introduction. Question 1A, feature engineering. So the first thing we have to do is we have to convert these features to numerical values. So it says a straightforward approach is to map some of these features into numerical ones. So for example, day, we can have 1 to 7. For example, Sunday can be 1, Saturday can be 7, or whatever it is here. The problem with that, as it says right here, is that that means that whatever I assign to 7, that's now more valuable or more important than whatever we assign to 1. But we don't really know that. That's probably not true. So we don't want to make Monday 7 and Sunday 1 or whatever, just because that's going to introduce some assumptions and some biases into our model that we'd rather not have. So that's why we use one-hot encoding. So instead of just having one number, now we turn our column into a vector, essentially, with 7 different entries. And they're all going to be 0, except for the one that is actually the case. So for example, in this example right here, if this was Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, so on, if the day was actually Sunday or Saturday or whatever, then all of these would be 0, except for the one that it actually is. So I think whomever wrote this lab must be from Britain or something, because they made Sunday the last day of the week. Really, Sunday is the first day of the week. But for example, they say, oh, if Sunday was the day, then all these would be 0, except for the last one, indicating that Sunday is 1. So that allows us to use these categorical variables without introducing anything we don't want to introduce. So the very first question that we have to do is we have to literally write this code that one-hot encodes our data frame. So here's what the data frame looks like. Somehow we have to turn all of these columns into this form. So this is a pretty hard question right off the bat. They don't, in kind of other labs, we kind of give you skeleton code and we kind of build you all the way up. But here it's right off the bat, just write the whole thing. So before I dive into the code, does anyone have any ideas as to how to start this problem? Obviously, I don't expect a full answer, but just generally, like, um, just like where should I begin? Can we use PD get dummies? Um, yes, technically, but we discourage you from doing so. Um, yeah, John says, brings up an excellent point. There's one function that basically will do this all for you, um, called PD.getDummies, but we don't want to just like, we kind of want to walk through the actual steps of what you're doing. So while technically you can and you'll get full credit, we discourage you from doing so. Kieran says, maybe identify columns that are categorical. That seems like a great place to start. So we could do this with code, or we could just literally write the names of the columns that are categorical. So I'll call them categorical columns equals, what is it? It's sex, smoker, day, and time. Now, what should I be doing? Any tips on what to do now that we have these columns? What I would do is clearly we need to do some kind of iteration here. And I know a lot of times in this class we discourage you from using for loops. But in this case, I really want to use a for loop. So here we go. Here's a for loop. So for a column, let's say in categorical columns. Then what? Well, the thing that comes to mind is that I'm going to want one column for each of the possible values in the original column. So for example, sex, it's quite easy. We just have female and male. So we need like a sex equals female column and a sex equals male column. For day, it's a little bit more challenging. We need 7 for each of the 7 days. But somehow I need to figure out all the possible values in this column, in each column that we're iterating through. So what I can call, is I can say like, oh, entries, or like possible values or something. And we can say, we can use data column to get the series that represents the data for each of the column. And we can call dot unique. And what dot unique does, in case you don't remember, or in case we never explicitly covered it in the pandas unit, it just returns a list of all the unique values in a series. So for example, if I wanted to just print this out, I could print, just print column and then entries. And then we can see, oh, great, for sex, we have female and male. For smoker, we have no yes, day. There's actually only 4 different days in this data set. I guess they didn't record any data for Wednesday or something. And then there's 2 possible times, dinner and lunch. So now what I need to do is I need to make a new column for each of these combinations. So you have sex female, sex male, smoker no, smoker yes. We're going to need a new column for each of these. And what I would like to do is we go the easiest way to make a new column, I feel, is just do data and then give it a name. For the name, it's really up to you, but in this case, you can say column and then say plus, like an equal sign, plus entries. But I made a mistake. Sorry about that. Of course, we need to iterate through all the possible entries, entries and entries. And then we can make a new column like this. Is everybody with me so far? Any questions at this point? Yes, yeah, exactly. Oh, thank you to the comment in the chat. Yes, little mistake there. And then, okay, great. So what should we set this column to be equal to? Well, we want it to be 1 if if like the value is actually that value. So if the sex is actually female, then we want it to be 1. And if it's not female, if it's male, then we want it to be 0, at least for the sex equals female column. For the sex equals male column, it would be vice versa. You could do a list comprehension. That's one way to do it. In this case, we like to use vector operations with series. So one way we can do is we can just say data column, which again is our series of data, equals entry. So for example, we can, instead of printing this, we can print column entry. So now we go through for each of these column entry combinations, so sex female, sex male, smoker no, and so on. What we're checking to see is if the sex column equals female. And then in our next iteration, does the sex column equal male? And if we want to, I'm not sure if this will work, but we can try. And we can see for the sex female column, we get a bunch of true, false, male, false, true, smoker, and so on and so forth. And if we want just like as a diagnostic check, you can go back to our original data and see, oh, the first and the fifth are both female. The first and the fifth are both true. So that's something we can do. But we don't really want trues and false. We can just convert these trues and falses to integers, and just, we have a series here or an array, and we can just say, hey, instead of Boolean, I want these to be integers. So now if we do that, if we like print that here, we see 1, 0, and so on. And then the last thing we need to do is that if we return data, because again, we added everything on to data, we see our data frame here. It looks like we one-hot encoded properly. We have columns for each of the sex equals female, sex equals male, day equals Sunday, Saturday, so on and so forth. What's one last step we need to do in this function? I've been kind of talking a lot. So here, yes, someone says, drop the other columns. Awesome. So what we can do is we can just say data equals data.drop. Always make sure to assign it to what you want it to be assigned to. Otherwise, you're just doing it, but you're not assigning it to anything. Or you can use the in place equals true argument, but I don't like doing that. That's pretty dangerous. But anyway, yes, we have to drop these columns, and we can just drop the OG columns. That's this list. And to tell pandas that we're looking at columns and not rows, we have to say axis equals 1. If we wanted to drop rows, we'd set axis equals 0. But there's no rows that are named sex, smoker, day, and time, and we don't want to do that anyway. So that's what we do. And then now we see, great. We have total bill, size, our two like numerical features to begin with, and then a bunch of one-hot encoded questions. And then do we pass the test cases? Yes, we do. So any questions about 1A? Really quickly, while we're still on 1A, I'll tell you that this is not the staff solution. And I'll go over here if I can get this stupid Zoom menu off my screen. This is the staff solution. And to me, it looks like gibberish. We use this dict vectorizer tool. We take our columns and we convert them to a dictionary. Then we transform and then convert back to an array. This makes no sense to me. And we're never going to ask you like on an exam, like anything about dict vectorize or anything like this. So if you want to do some research on your own about how this works, that's great. But it's not really super important. Personally, I find that this is a lot more intuitive um, than um, than this. This one just looks really weird. It's like I don't really understand it that much. But if you have questions about how this specific solution works, you can just post on Piazza or whatever. Yeah, Jessica did a good point in the chat. In practice, in the real world, you can probably just use pd.getDummies. It'll make your life a lot easier. But for this question, we wanted you to make sure, like, we wanted you to explicitly do it, as Jessica said. So if there's no more questions about 1A, I guess if you do, you can throw them in the chat. We'll move on to 1B. So 1B says, now that all of our data is numeric, great, we can begin to define our model function. It says, now that we've one-hot encoded, instead of the 6 features that we had before, there's now 12. And you see like what our model becomes now. Instead of just time, we have time lunch and time dinner. We can represent the linear combination above as a matrix vector product. So we can write this function, linear model, which takes in these thetas. You can think of thetas as the weight, like the weight that gets assigned to each of these different features. And then x, and x would be our design matrix, which would be have like all of our inputs, which is this. Does anyone have any ideas how to go about this question? We're literally just taking the linear combination of thetas and features. Yes, we do np.x at theta, return x at thetas. That sounds good to me. So let's try np.x thetas. Great, that works. Or we can do x at thetas. That works. Or you can even call thetas, or x, which is our matrix, x dot dot thetas. All 3 of those work. It's not really important which one you use. There's like subtle differences between them and how they're actually calculated. But for all intents and purposes, it doesn't matter. So I guess, yeah, if this works, we'll move on. Yeah, the one thing you don't want to do is you don't want to do thetas at x. That will not work because you did the matrix multiplication in the wrong order, and we won't get the expected output. Great. So now we're on to question 2. Recall in lab 6, we defined multiple lab functions and found the optimal theta using the minimize function. Here are these loss functions again. We have the L1 loss, which is obviously the absolute value, and then the L2 loss, which is the squared error. These should look pretty familiar to you. So we want to write this function called minimize average loss. So we said minimize the average loss calculated from using different theta vectors and estimate the optimal theta. So we take in a loss function, which could either be L1 or L2, or something else if you wanted to define something else. A model, which would be something like this function that we called earlier, that we made earlier, but it doesn't have to be. That's why it's an argument in our function. And then x, which is our data, and then y, which would be our response variable, in this case, tips. But since we want to generalize, that's why we write a whole big function here. So there's a lot of like hints here. So we want to fill in this first ... should be replaced with the average loss evaluated on the data x and y using the appropriate model and appropriate loss function. So I guess let's just start with that. Any ideas on how to begin? How would we calculate the average loss given these 4 arguments? Yeah, how would we calculate our average loss? You don't have to give the exact line of code. Pretty long, but just generally Any ideas? So someone says we can do np.mean, loss function, y, model of theta and x, and then we close our parentheses like so. And yeah, I think this would work. We have our loss function, which takes in two arguments, y and a y hat. So we have y, and then the way we calculate y hat is by taking our model function of theta and x. And then once we have our loss function, which will be evaluated for each and every individual data point, then we take the mean. And yes, there's a question in the chat. You did the subsetting, and it gives you true and falses. Yes, the way you convert to 1 and 0 is with as-type int. Or you could use float if you really wanted to. Doesn't make a difference. But yes, that's a good question, and thank you to the chat for hopping in. So that looks good for the first like blank. Hopefully it works. Any ideas on what to fill in here for our initial guesses? Bennett says just a random vector. Sure. Personally, I forget the exact syntax to make a random vector, but you can call, you can even like just set it to 0. And yes, it has to be the same length as x. So we could call, yes, x dot shape 1. So we could just do zeros, or we could do, as John said, we could do np dot random dot random. And either of these will work. We can make them ones if we wanted to. We can make them whatever. It doesn't have to explicitly be a random vector. So we do that. Hopefully this works. And you see we run, we get some weights. That seems that like these are our weights. There's not really much else to say about that. Like that's what we got to minimize the loss function. And then we pass the test case. And like I was saying before, you could do zeros, same thing. But do notice how you get different values here. And that's something we'll be investigating later in the lab. You need ones, same thing. The difference between rand and rand-n, I'm not entirely sure. You just did rand. Yeah, that's something you need to look up in the documentation. I'm not sure off the top of my head. So any questions about question 2 or anything from before I hand it over to Jessica? X naught or X0? X0 is our initial guess as to what our thetas are. So there's a note here. It says the optimization people like X to be the thing that they're optimizing, even though obviously it's theta in this case. It's just the argument is called X0, and that's just our initial guess. Because most minimization algorithms, especially the one that we'll learn in a very short time, you start somewhere and then you minimize from there. And we need to know where to start. So we just start at a random place.
You can kind of think this as like this function is sort of doing like a guess and check type of thing, but more educated guess based on like a particular algorithm. And we use this when we can't really use like pure math to do like, imagine trying to do it by hand, and if you can't, you kind of do it like iteratively and like try to find a point.
Another question, what is model of theta x? So model would be when we pass it in, when we actually call this function that we wrote, we pass in linear model here. And linear model that we just defined before is a function that spits out a prediction, or in this case, like y hat, our prediction given some weights and given a row. So in this like math expression here, given the thetas and given the values for size and total bill and so on, it'll calculate tip. And yes, technically, for those of you who remember 61A, these are like higher order functions because we're passing in a function as an argument to minimize average loss. So if we really wanted to, we could just get rid of this argument and just call linear model directly here, but that's not the question. So does that help answer the question? Did we define the theta here? So the theta is going to be the output of this whole minimize call. So the minimize is just saying, hey, find the theta that minimizes this lambda expression. And then the theta that we start at is our random, like a random vector. And then given how we calculate loss, this will calculate our loss, find the theta that minimizes loss. And that's what minimize does. It comes from this module. Yeah. So this function here returns theta. All right, great. I guess with that, I'll hand it over to Jessica. We'll take you through question 3. You need me to stop sharing?
Yeah. It's this one. Can people see my screen?
I can see it.
Okay, great. I can't really. My computer is very small, so I don't think I'll be able to see the chat as clearly. But okay. So for question 3, we're gonna be fitting our model analytically for L2 loss. And as you recall, L2 loss is the squared loss. So we're gonna be doing y minus y hat, and then we're gonna square that. And so for this, we're basically solving for least squares. And for those who want to see the derivation of it, the lecture will probably have it. But for the optimal theta hat, which is the vector of all the weights for the features that we want, it became x transpose, the dot product of x transpose x, and then taking the inverse of that, dotting it with x transpose again, and then with the y. Based on this equation, we need to find what theta hat is in this equation. So does anybody want to take a stab at this one? It's very similar to the ones that you've done before, where we give you an equation and you kind of just use it. Is it just linear? Yeah. So for this question, someone said that we can turn the np dot linear algebra dot inverse of this, and let's take a look. Okay, yeah. So as you can see that we have we're taking basically the inverse of the x transpose with x, so that's this part. And then we're gonna dot that with x transpose y, which is this part. Does anyone have any questions on 3A? No? Okay. yeah, it's just a direct translation of what this equation is. So if we run it, we see that there's an error, right? The analytical thetas, we try to get the analytical solution from the one hot encoded we created in question 1 with tips. However, there's an error. And what the error says is that, let me see. The axes parameter is not supported by the implementation of transpose. Okay, so I guess for this one, transpose might not be working, but we can fix that very quickly. I think instead of multiplying, I think we need to do the dot product. So let's try doing that and see if that works. The function object has no attribute to dot. Okay, that's interesting. We're supposed to transpose x instead of y.
If you just do x dot t, it should work.
Yeah.
Or if you want to do transpose and then open close parentheses.
Let me see.
Doesn't really matter.
Okay.
Yeah.
Okay. Yeah. Thank you. Yeah, the dot t. I'm not entirely sure why the dot transpose didn't work. I think it's just because of the parentheses part. But yeah. Great. Okay. As you can see, if we run the cell for analytical thetas, we get these numbers, which if you look at it for like 1 second, it looks okay because they're kind of small, but you can see that they're exponented to great magnitude. So this one is like to the 17th power. That doesn't make sense if they're weights, right? It just, yeah, the weights are way too big to be weights. And so does anyone want to take a stab at why they might think that this analytical solution that we derived in lecture doesn't work for this question? No? Okay. Well, so the way we can get, so someone wrote X has linearly dependent columns. So X transpose, the dot product of X transpose X isn't full rank. That's correct. So for this, it wouldn't work because we have linearly dependent columns. And what that means is that if we looked at the this like data frame that we made before, one of these columns can be inferred from one of the other one or more of the other columns, right? So like as a small example, like female can be derived from the male column, right? Like if male is 0 and like, which means you're not male, then that means that you are female, like just by inferring that. And that's therefore that these columns are linearly dependent. But the only way we can do it analytically is if all the columns are linearly independent. Does that make sense for people? Can I get like a thumbs up or a yay or a no? Okay, I guess yay, okay, great. So we need to fix this in our one hot encoding. And so I'm just gonna copy what we had before. I'm going to copy from part 1. So, because we just need to adjust it for this. Okay, so we have these. Does anybody want to give me sort of an idea on how maybe we can make these stop being so linearly dependent on each other. Drop sex, smoker, and day. Instead of having is female, is male, we could just have an is male column. Yeah. So from the responses that I see from the chat, a lot of people are saying drop some columns. And that is right. There's many ways to this question. So one way that we could do it is that instead of iterating through every entry, we would just skip one of them. So we would start from the second element and we could run that. And now, yay, it's giving us like our analytical and numerical, like that are basically the same. Yeah, they're like close enough to be to each other. That's one way we can do it. There's other ways too, like you could start from like the -1 at the end. That would also do the same thing. Alternatively, you could just write, as Isaac said, let's say that this was a little bit too confusing. We could also just keep what we had from before and then manually just do data equals data dot drop. And then we specify which columns that we want. Does anybody want to tell me which columns specifically that they want to drop? Okay, we have sex equals male. Why is it not typing? Okay, sex equals male. Smokers equals yes. Yes. Oh. You ended up getting a really large analytical loss. How big is your analytical? 2,364. Oh. Isaac, a lot of people are getting different losses for some reason. I got 100.
For your analytical loss, people are getting these extraordinarily high values.
Is that for 3B or is it for 3A? Like, because if it's for 3A, then it still makes sense because those are ridiculously large numbers that shouldn't be weights. Oh, okay, some for 3B. Wait, can someone tell me what they did for 3B?
What did people get for 3A?
Yeah.
Because we might be exposed here. To be honest, we were having some issues with this lab beforehand. Depending on, yeah, that's exactly what I figured. Yeah, we're really sorry about that. Yeah, we're getting exposed, Jessica. Basically, the issue is for some reason, when we were testing this lab earlier, Pandas doesn't really like our solution for, I guess, my solution for 1A, the very first question. It almost, yeah.
It basically broke Pandas.
Yeah. So what you're getting, it still kind of makes sense in that you're getting numbers like -96 or 64, 96 that don't really make sense. So they might not be like e to the negative e to the 17 or whatever, like on the magnitude of 10 to the 17th power. Um, but um, but yeah, so it's just a weird pandas quirk that we couldn't figure out. I'm just gonna be honest here and say that for 1A, the
Do you want me to
the
scroll to
solution
one?
that we presented to you, it gives you the exact same data frame that that like the staff solution does, the one that I presented to you for like 5 seconds. But for some reason, it doesn't like it's not handling the rest of the questions very well. So if you want, Jessica, do you have the staff solution up, or should I?
I have it, and I have both, but I think regardless, I feel like, well, one, this one isn't really like there's no like hidden test for this or even any public tests. But should we show the staff ones, or because I think yours
Because there is 3B. There are test cases for 3B that they're gonna not pass.
Okay.
I guess yeah, we should have. We got definitely exposed. Yeah, I'm really sorry about this.
Okay. Okay.
Do you just want to share it, or should I?
Wait. For 3B, it doesn't pass, but I'm using your code.
That's the thing, is that my code, it works, but it doesn't pass the test cases for some reason. And we should have realized this before.
It passed here.
Hold
up, like.
Yeah. Why does that?
It does pass. I don't like. Let's say we did.
If you do one, does it still pass?
Yeah.
Wow.
So if you only typed up what we did previously, which was like dropping only the 2 columns, we weren't done with that yet. So that could be possibly why it doesn't work.
Because they're getting the negative 96 though, which is what we were getting before.
I know, but like 3B should still pass. Like we didn't finish this part, the part that I highlighted. Like you're supposed to be dropping more. Like day. Someone pick a random day. I'll pick Sunday. Okay, great.
And then you need.
And then we need time.
Time equals dinner.
Okay, time equals dinner. Like it should still work. 3B, the test doesn't necessarily depend on 3A because our 3A code works. 3A was just to like lead into the 3B reasoning. Yeah, we just needed to drop more columns.
Yeah. Yeah. So if you're getting like weird like 96 and whatever, then for 3A, then that's fine. But I want to make sure people are passing the test cases for 3B.
I thought data.drop categorical value. This one is out of the for loop. Oh.
Well, because there I'm just dropping it one by one. You could just drop the whole thing at the end, like all of categorical columns.
Oh no, it has to be in the for loop because the for loop goes through column in categorical columns. If we pulled this out, it wouldn't know what column is. Did it fix a problem because it made them independent for 3C?
Yes, yeah, move on to 3C, yeah.
Yeah, sorry. Yeah, so why did removing redundancies in our one hot encoding fix the problem? It's because it made the columns linearly independent again, which is what we wanted. Yeah, because okay, I have 5 minutes to explain this. Yeah, okay. Made columns linearly. Yeah, don't write this like shorthand everything. This is just so people can see it in case they didn't catch it. But it made columns linearly independent again. And the like intuition behind all of this was that if we kept all the columns, so we kept like male, female, and then all the days we had, and then all the times we were looking at, we would be getting into a thing called the dummy variable trap. So yeah, I'm just gonna write like the notes. And what this means is we're literally keeping like every column, and that doesn't work because for 3B, I'm getting an error that says singular matrix. That's totally fine. That error
That's a 3B.
can also happen. And what that also means is that because it's a singular matrix, it means that it's a square matrix without an inverse. And because without an inverse, it just means that they're also like the columns are linearly dependent. So it goes to the same conclusion. If you're still getting error for 3B, you have to drop more column. Drop outside the loop. I mean,
Jessica, I'll handle a chat if you just want to explain.
Okay.
3C, yeah.
Okay. But yeah, so dummy variable trap is when we keep every column, which is what we had in 1. But like the issue with this is that when we're doing these like multiple variable regressions, like the betas are telling us like this variable is increasing the y variable that we wanted by some certain amount, but we need it to be compared to something. And that compared to something is the things that we omitted from the regression. And so let's say if we had something that looked like this, so like y is equal to like theta 0 plus theta 1 times like male, and then plus theta 2 times female. Like, what is the omitted, I guess, gender for this question? Assuming that we only have 2 genders. But like this doesn't have a comparison because we included female and male in our regression. And so this is why this is a dummy variable trap. It's because like I like these weights, like I don't know what they mean because I don't know what I'm comparing it to. And so we can delete one of them. And therefore I know, let's say I got something that was like 0. Actually, let's just do 10. And then remember y is like tips or something. Then what this is saying is that like compared to females, males tip $10 more. And like because we omitted that one extra column, we now have something to compare to interpret our regression. Does that kind of make sense for people? I'm assuming so. Okay. But yeah, that's just the general idea behind the dummy variable trap and why we can't have it. 3B is this one. Yeah, we can go. Isaac, do you want to go over the first question after? Is everyone done with? Can you explain the question right after 3A? Okay. Let me see if I can like this one. Well, the idea behind it was that the columns are linearly dependent, right? Like, and the only way we can take inverses of matrices is if all the columns are linearly independent. This should be from like linear algebra class, but okay. If you have individual lab like coding questions, feel free to post a private post on Piazza. Technically, this lab is over, so for those who need to go, they can go. Yeah, but Isaac will go over 1 as soon as we wrap up this for 3A, 3B, and 3C. Do we have to do linear algebra solve for 3C? What do you mean by linear algebra solve? Oh, I mean, this thing? Oh, they're just two different ways to do it. This is optional. Uh, but like, yeah, they'll do the same thing. But with redundant features, like the linear algebra solve will like do what you wanted it to do, which is drop the redundant ones. Okay, Isaac, I think you can go over question 1 again.
Okay, great. Sorry again for the confusion, guys. If you are struggling, for some reason it's not working, yeah, please make a private Piazza post or even go to office hours. Yeah.
Yeah, office hours,